Next, we're going to look at the log-normal distribution. This tends to confuse students frequently because the log-normal distribution is very similar to the normal distribution, except we're looking at the natural log of x. So for the PDF of the log-normal distribution, we have what's given here. And you can see that the PDF is very similar to the Gaussian distribution. The log-normal distribution has, again, two parameters. We have this lambda parameter and this zeta parameter. But notice that for the log-normal distribution, this is valid for values of x greater than 0. Your textbook has an error in the equation that says greater than or equal to 0. In fact, we cannot be equal to 0 because we have the natural log. It's an infinite result if you take the natural log of 0. So stretch that out in your textbook and just write greater than. For all values greater than 0, we have this PDF. The two parameters, lambda is the expected value of the natural log of x, and zeta is the square root of the variance of the natural log of x. So these, you'll recognize, are the mean and the standard deviation of the natural log of x. So not just x, but the natural log of x. And I think this is where the confusion comes in often. So here's the PDF plotted up for different values of zeta of our log-normal distribution. Notice that we are positive in all of our x values. So this differs from the normal distribution in that we only have positive values. We start just above 0 and we go on to plus infinity. For these plots here, the median value of 1 is used for illustrative purposes, and later on in the slides here you'll see why we use the median instead of the mean to describe the location of the log-normal distribution. So this parameter zeta, which describes the standard deviation of the natural log of x, as we increase it, we see that we flatten out our distribution. It starts to spread out, just like the normal distribution does. But notice that with increasing values of zeta, the values not only spread out, but the skewness of the distribution increases. So as we go from 0.1, we have this kind of peak. Then we go to 0.3, we start to skew. So most of the values are to one side. And as we go to a half, we increase even more. So the skewness even it causes the distribution to be lopsided to one side even more. Later on in the textbook, it is derived that if x is log normal with parameters lambda and zeta, then the natural log of x is normal with mean lambda and standard deviation zeta. So if x is log normal and it has parameters lambda and zeta, then the natural log of x is normal with the mean lambda and standard deviation zeta. And this derivation is done in a later chapter, but it's useful for us now to introduce this because this allows us to use table 8.1 if we have a normal distribution. We can still use the tables. But we need to do a little bit of a transformation. So here we've got the probability that x is greater than a and less than or equal to b is simply going to be the integral of PDF, in this case the log normal PDF. And we make the transform by substituting in s for what's in the parentheses, natural log of x minus lambda by zeta, and we change dx to zeta x ds. And then we end up with this result right here, which looks an awful lot like our standard normal distribution, where the table is derived from. The table 8.1 in our book is derived from. But notice the limits. The limits change such that we're taking the integral now of the exponential function of a minus 1/2 s squared ds from the natural log of a minus lambda divided by zeta to the natural log of b minus lambda by zeta. So this is the form of the standard normal distribution with the CDF function going from the natural log of a minus lambda by zeta to the natural log of b minus lambda by zeta. So we use the CDF function of s, what's in the parentheses, the transform, in order to be able to use that table 8.1. Because they are related, and through the natural log of the random variable x, we can go from parameters of the normal distribution to the parameters of our log normal distribution. And the relation that is derived in your textbook, and I'm not going to go through that, you can look at that if you're so curious. The mean of the normal distribution of x is equal to the exponential of the lambda plus 1/2 of zeta squared. And we can rearrange this such that we get a definition of lambda in terms of the mean of the normal distribution. Zeta squared can be found as the natural log of 1 plus the standard deviation by the mean squared, which is the coefficient of variation. So we can reduce that to the symbols used in the book, the natural log of 1 plus the delta x squared, this being the coefficient of variation. Your textbook also discusses a simplification. They say that when the coefficient of variation delta x is less than or equal to 3, then we can make the approximation that the natural log of 1 plus delta x squared is approximately equal to delta x squared. And therefore, because this term here is zeta squared, right? This is zeta squared is the natural log of 1 plus delta x squared. Since these two are equal, essentially zeta is equal to, or approximately equal to, the coefficient of variation for this case. And what I've done here is I've made just a quick plot of delta squared versus, or natural log of 1 plus delta squared versus delta squared. And we see that for values of delta equal to 0.3, this is in the square, so this is 0.09, one end here, it's a little bit cut off. The black line is the one-on-one relation, and the blue line is this approximation, what we actually get. And you can see for higher values of delta, when it approaches 0.3, it's a little bit off, but not bad. And then as we get smaller and smaller values of the coefficient of variation, the error becomes another order smaller. So it's not a bad approximation. Your textbook uses it, and that's why I bring it up. If I had my way, I would probably never even introduce that. There's no point in making the approximation when we have easily can do this calculation on our computer or handheld calculators. But this is just a simple approximation that they use. And they utilize this in some of the examples and the problems. So if you get stuck and you have you're given the coefficient of variation and talking about a log normal distribution, then chances are you better check this condition, because that's what they've used to help solve the problem. So keep this in mind. Now we use the median to describe the log normal distribution instead of the mean, and we do that because it's a more indicative of the central mass, whereas the mean is not going to be. So let's look at what the median is in terms of the log normal distribution. We've got the CDF function of our S transform, which is the natural log. In this case, we want to find the median, so x median minus lambda by zeta is equal to 1/2. That's the definition of our CDF. So we take the inverse CDF function of both sides. The inverse CDF function of 1/2, use your tables, that's the first entry, is 0. And we have the natural log x sub m minus lambda by zeta. So we just rearrange, and we end up with lambda is equal to the natural log of the median, or the median is equal to the exponential of lambda. So when you're given the median, automatically you're going to get your parameter lambda, or vice versa. If you have lambda, you can go ahead and find the median. It's a nice relation, nice result of the natural log distribution. Now your book goes ahead and derives this relation by combining a couple sides of some equations that we've already seen, but really the punchline here is the mean value is going to be equal to the median times some positive parameter. Right? We've got a square and we're adding 1 to it, and we're going to take the square root of that. It's going to be positive. So what that tells us is that it's going to be greater than 1 as well. What that tells us is that the mean value is always going to be greater than the median. So the median is going to give us an idea of the central value, whereas the mean really doesn't give us a good indication of where we are and what our distribution looks like, how skewed we are, or if we're not that skewed. It still is going to be greater than the median. So as a result, what we do is typically describe the log normal distributions as with the median parameter instead of the mean. But keep in mind, these are all related to each other, and they can go back and forth quite easily. At this point, take a look at the videos for examples 3.12 and 3.13.